Hello everyone. Are you able to hear me? Can you unmute and respond whether you can hear me or not?
Yes, sir, I can hear you.
Okay, yeah, thank you. So let's start today's session. I'll share my screen. Uh, okay, yeah. So I hope you can see my screen. With we'll start with a discussion based on week 11 lectures. Uh, okay, so what was done for week 11?
So in week 11, many convolutional neural networks are discussed and self-organized maps.
Yes. So yeah, it started with artificial neural network for pattern classification. I mean, everything is a pattern there in data, and our neural network tries to get that pattern, and based on that, it will generalize to new data, whatever it has not seen during the training time. So that's the core idea of using the neural networks or even machine learning as such. So neural networks have recently become powerful because of various reasons we discussed last class. Here in these lectures, the few specific ways of using the basic neural networks, and at the last, some parts of deep learning was also discussed. Okay, so the basic neural network was mostly uh, inspired from the neurons in our brain. So it has many receptors, and then it takes the input from many receptors and then tries to process it and then gives one output. This is done by just one neuron, and there are millions of neurons in our body, due to which we are able to function like this. So, if we want to have some sort of intelligence, the computer equivalent to be should be take multiple inputs and then somehow process it, which is generally the summation in our case, and then add a nonlinear function, which then gives an output. So that's the basic model of an artificial neuron. So in our basic model, we have the sum inputs, multiple inputs. Each input is a scalar here, and then each of these input will be scaled by a weight element W. And after scaling, all of these inputs, the scaled inputs will be summed up. Once you sum up, you take a function which non-linearly maps the input to output, which is called as squashing function in general. So sigmoid is one of the squashing functions because why is it called squashing function, by the way?
Because it brings some non-linearity in a net in the inputs. Be- and
Non-linearity is fine, but anything more than that, why is it called
because
squashing?
because the in sigmoid function after a certain threshold it gives a value as 1, and if the value is below that threshold it will give you the value as 0.
No. So your sigmoid function looks like this. Sigma of x is your sigmoid function. It looks like
1 upon 1 plus e is to
it's
power
got
minus x.
yeah, yes. This is the sigmoid function. So if you have this function, there is no threshold here, but your function. Uh, okay. So your function at x equals to 0 is what? How does it look? X equals to 0 is half, right? Place x equals to 0 here, it will give you half. Place x equals to infinity.
X is equal to say,
Infinity means
infinity.
this part will be 0, then it will reach to
It,
1.
it give you the value as 1.
Yeah, it will reach here as 1, and we place it as minus
Minus,
infinity.
it will give you as value as 0.
Yeah, because this part goes to infinity, so the denominator ultimately goes to infinity, so the numerator will go to 0. So at some point it will go to 0. So your function will look something like this. Yes. So what it is trying to do is, yes, you are right that it non-linearly maps x to this space between 0 and 1. So it's squashing because it maps everything from minus infinity to infinity between 0 and 1. So that's why it's squashing. So it maps minus infinity to infinity to 0 to 1. So this is the input domain and this is the output. So since the output is bounded between 0 to 1, it is a squashing function. Okay. So of course there are many types of neural networks, and in neural networks as well there is supervised learning, which is most commonly used uh, way with neural networks, but you can also do the unsupervised one. So in supervised one, again, as we saw earlier, that we'll have labels, or we have the outputs known to us, and we have input output pairs. Based on that, we will try to minimize the error. But in unsupervised learning, we don't have any output vector given to us, or any sort of output given to us. So what we need to do is we need to just find patterns from the data directly without any known output. It's mostly used for clustering, as discussed in the class. So when you want to cluster data, you don't really need to know which cluster it belongs to already. So you can just cluster based on the specific distance metric that is defined. Okay. So once this is done, a few basics about neural network, yeah, basic neural networks were given, and how neural networks help achieve the nonlinear boundary. So as I said that if your data is in the previous session we discussed that if your data is non-linearly separable, so what are the two methods that you can apply? The first method is uh, project the data into high dimensions, into higher dimension where the data can be linearly separable. So this example was discussed in the last discussion. Uh, and the next one is uh, develop or model a nonlinear classifier. So here in this specific case of neural networks, we are doing this. So neural network does this instead of doing the uh, data processing into higher dimensions. So it directly develops a nonlinear. Well, neural network is a nonlinear model because of the nonlinearities that we add. The one of the examples that we saw is sigmoid, which is a squashing function. So based on this, we develop a nonlinear classifier. Okay, so that's the core idea. And after that, there were a few examples given on decision boundary and how does it help to classify some basic functions. And also based on that, there was a nearest neighbor classifier given in the form of neural networks that was discussed in the class. So once this was done, we we looked into some of the basic aspects of training neural networks. The first one is about the first part discussed is about how what are the different neural networks out there. The first is feed forward neural network, the other is feedback neural network, and there is so for feed forward neural network. in a single pass, the inputs flow only from in one direction. That is uh, feed forward neural network. So in this case, what happens? So if you have some input neurons and then some hidden layers, and then we have some output neurons. This is input layer, this is output layer, and yeah, these are the hidden layers. So when you have connections, the connections, the data only flows in this direction. So you have all possible connections if it's a fully connected layer. So generally these are all fully connected layers. And based on that, what you see is the flow of data goes from input layer to the output layer. That's what is meant by feed forward. Of course, during training time, you propagate the errors backward, but your input propagates only in left to right direction, rather input to output direction. That's why it's called as feed forward neural network. So the next one is feedback neural network, where if I say something like this, so there will be a special neuron, for instance, which takes the output in some fashion. Maybe there is some uh, operation out here, probably the sum of the two outputs, and then it feeds to this neuron, which is then connected to each of these. So this is the feedback connection, the green one that I'm showing. So in general, it is well known that if you try to keep a feedback loop, it is not stable. Can you give me an intuitive reason why it happens? Anyone? So what I'm saying is that the feedback connection may not always be stable. Why do you think should be the case? So I'll give you a very simple example that might help you understand this concept. So if your gain, for instance, if your input is a single dimension and output is also a single dimension, then uh, so this output is, or rather OI plus 1, if I give OI plus 1 is a function of maybe a function. I'll not write function explicitly. Maybe that function is also a scalar multiplication. So it will be G times input at I plus 1. Okay. Well, input should not depend on this, but output will be like this. And if there is another gain factor H in the feedback loop, so it depends like this, O into I. Yes. So this is the current output. This is the input, which which could be fixed, but this is the output coming from the previous time. So once this happens, so what if you take OI plus 2? OI plus 2 is again the same thing. G into I plus H into OI plus 1, which is G into I plus H into OI plus 1 is this G into I plus HOI. So as you see here, it will be G plus HG times I plus H times OI, H square times OI. So these, if you see, if this factor H is greater than 1, so if you do I enough times, your output will blow out. Yes, it can go to infinity. So generally speaking, this feedback connection is not that stable, but of course, a special case is the RNNs where people have made it to use really well. Okay, so the next one is the Hopfield network. So what happens in Hopfield neural network? So every node is connected to every other node. So it's not really like you can draw a flow from one the input to the output. So here you might have one node as input and the other node as output, but you have connections going across in all the directions. So you have all possible connections from all the nodes. So that's how the Hopfield network is defined. And competitive network is something we'll look, we'll have a problem on this as well. So the competitive network is generally used for clustering. So it can see that how your input and output is matched properly in some specifically used for clustering in the sense that if your weights match the input, then they give a good output, specific output, and other one of the neurons will give proper output, and the other neurons won't give output. Anyways, we'll look into one of the examples that's done in the assignment. And then there is self-organizing network where the maps itself are defined. Yeah. So the maps between input and output are defined in such a way that they make some meaningful sense in this space. For instance, if your inputs are like this, here are the inputs, and if you have some connections from here to here, and maybe some connections from here to here, some connections from here to here. So, for instance, if these two attributes x1 and x2, and maybe this is some other attribute xk, if x1 and x2 have some similar attributes, so they might be connected to a nearby region. And if x2 and xk are shows different attributes, for instance, uh, okay, I'll take the example of humans. So, for instance, height and weight should have some relation if a person is healthy. So they should have some similar attributes. So in that case, they might be in this region. But weight and hair color won't make any sense. So they may not be nearby. So they will be at some other place in this array of connections. Okay. So that's what is self-organizing unit. Okay. And then the supervised learning case uh, is something that you might have gone through in other courses. Like when you have supervised learning, you have a backpropagation algorithm from where in which you have known outputs. From known outputs, you take the error difference. Once you have error difference, you can propagate those errors using the backpropagation algorithm. So the backpropagation algorithm, in short, is just a chain rule as to how to propagate the errors at the output layer to the intermediate layers. And during this, the weights of the neural networks are updated. Okay, so yes, there are a few other things as well which are discussed based on unsupervised learning, which is one is competitive learning, one is frequency sensitive competitive learning, and the other is coherent neural networks. So the coherent neural networks, we have one question which we'll discuss. Yes. Okay. So at last, a few advantages were discussed on why neural networks are useful because they are inherently parallel. That means if specifically if you see the case of feed-forward neural network, all these operations in a single layer can be done parallelly. And so what you are trying to do is instead of trying to get the whole function at once, so this whole thing represents a non-linear function, complicated non-linear function. What we did with this small neurons is that each small neurons will represent a small simple function that we saw, which is nothing but the summation of these inputs coming to it with some bias, and then we add a nonlinearity on top of it. Uh, and yeah, of course, there is one more thing that not everything can be modeled statistically or with math. So I mentioned this in last class that that's why any kind of learning method is useful. It's not specific to neural networks. Okay. Yeah, but with other methods of machine learning, we saw that there are some assumptions that were made to make it useful enough. But with neural networks, it's you don't have to make any such assumptions. It still works. Okay. So once neural networks, these are some basic parts of neural networks that were discussed, and then we uh, went to deep learning part. So why is it called deep, by the way? Can anyone tell me? So the deep here means that in our case of feed forward, for instance, we have many hidden layers present in our architecture. So if you have many hidden layers there, so if you see from input side, it looks very deep until you come out of the output side. So your tunnel is very deep. You can think of it that way. Okay. So the traditional methods are generally mixture of handcrafted features and then on top of that applying a few methods that we discussed earlier like SVMs to classify. But with deep learning methods, what we try to do is we try to learn the features as well. And why is it useful is because not every feature can be handcrafted. For instance, we have seen that Shift, we have to use so many tricks to make sure that it works under reasonable conditions. But still, it is not really the best descriptor, if you ask me. There are many other deep learning descriptors which are better working currently and is used in research purposes. Shift is also currently used, but the point is when your data is in extreme cases, then the shift tends to fail a lot. But the newer methods based on deep learning, they tend to work uh, very well. So based on your uh, application, you have different kinds of features, and you have to handcraft those features to get your pipeline working. But in this case, since you give an input as an image, your features will all, in case of deep learning, your features will automatically be learned. And how will it be learned? One way to do is through the convolutional neural networks. So yeah, we'll also discuss that specific part of it. But as also mentioned in the class, the traditional ML algorithms in general perform well when the size of data is small. But when the size of data is large, the deep learning algorithms perform well. So deep learning methods are generally data hungry in the sense that it needs lots and lots of data to generalize properly. But traditional methods, since we generally have some sort of assumptions, in case those assumptions break, it doesn't really work well. That's why it doesn't really work well with the size, even if we increase the size of data. in most of the cases. Okay. Uh, yes, there were a few examples given in the class, but I think I can skip through it. So, of course, your normal deep layer neural network looks like this. It's a feed-forward network. It could also be a feedback network, but in for the course, we'll only consider the feed-forward network in case of deep learning. So, in deep learning, this I'll just redraw it so that I can discuss a few more things here. Yeah. So, what we have is this is the input layer and this is the output layer. So all of these connections exist. So here also all these connections exist. I'm not drawing all the connections. The connections like these exist in the neural networks. Okay. So what a general deep learning network says is this is each of the layers are fully connected. Okay. So what generally these deep learning methods work well? Where do they work well? So for instance, we'll take the usual cat and dog classification. So you get some attributes, somehow some attributes. I'm not saying that you got it from a deep learning method, but if you get some attributes, for instance, the color and the shape and probably the color, shape, and maybe some other attribute that we don't know. So once you have all the attributes set up, you will just pass it through this neural network. What it does is it takes so each of this belongs to what? A class, either cat or dog, right? So each of them will have a feature vector. This is the feature vector where if I put x1 x2 xn, there are n features where the first feature I'm saying is color, the second feature I'm saying is shape and other attributes there. It's the same features, same features. I mean here also this first one denotes the color, second one denotes the shape and things like that. So once this is there, what is done with deep neural networks is you just feed all this. Uh, what do you do? You feed all this data into the neural network and then you train it through backpropagation. So this is what you do for a general data. But what happens in case of images? What if we feed images? So images are what? They are like arrays, right? They have like arrays and each of them will have some intensity values. So these are intensity values. So what I'm trying to say is they are not just a bunch of numbers, but what they are is the numbers are correlated. The numbers are correlated with the neighbors. So once the numbers are correlated with the neighbors, what it means is that it forms a pattern in this 2D space. Similar is the case if you take a audio signal. So if you have an audio signal, whatever is the amplitude that you get and whatever. So all these amplitudes will then are not just a bunch of numbers. You cannot reorder them. So there is an ordering involved. What ultimately this implies is there is an ordering involved in these kinds of data. So this is image and this is maybe audio. So both the cases there is an ordering involved. So you cannot just take each of them and pass it through the neural network as if you pass a single pixel in it. You can do that, of course, but it becomes highly complicated, not just in terms of number of parameters as shown in the class, but getting to find patterns is very, very difficult there because now you're working on very high dimensional spaces. So instead of treating them just as a bunch of numbers, what people have developed is the convolutional neural networks. So use convolutional neural networks or the CNNs. So once you have CNNs, what it does is we know it previously as well. It's like a mask. You just place the center at a particular pixel and then uh, do the integration or summation. Here we do summation because we are in discrete domain. Once you do it, you mark the response in the next array and then move on to the next area. And then mark the response and then move on to the next area. That's what we do. So, so we need convolutional neural networks, not just for images, but even data like audio to capture uh, some good attributes of the data, which correlates it with its neighbors. So, for instance, if you have an MRI data, then it will be a 3D data. It's not a 2D data like image. So once you have 3D data, your convolution should also take care that it's done in 3D. So when you do it in 3D, then you can ensure that your data has been captured properly, or rather the features extracted from these data is captured properly. So what we did is instead of just having this specific neural network, we'll have some convolutional layers. So your input will now be an image, and then we'll have a bunch of convolutional layers, and you can also do some max pooling or average pooling to reduce the size. And what after a point we get is this is the final feature vector, which is if this is 2D, probably we also want it to be in 2D or any dimension. It is not specific to the case. It is not specifically the case that we need it in 2D. It can be in any dimension ND. The point is once we have this final feature vector, now we append here convolutional, the usual neural network, and now these interconnections are there. So now this feature vector, what you're seeing, is analogous to what we discussed here in terms of the feature vector of cats and all, color, shape, and all. So these are some of the measurable things that we have developed color and shape. But the problem is, it will, we cannot measure something which is perceptible. Maybe uh, how smooth the fur is. We cannot really say it just seeing the image, right? But there might be some attributes. For instance, if the fur is very shiny, probably it's more smooth. So based on that, this final feature vector will take care into account some of those aspects as well. So a famous example of when it fails given is that uh, when wolves are found in many mountainous regions as well. So they have been classified as wolves not because the network found the eyes and the nose and the other features of the body. What it found is that the background is snow. So that's why it was able to classify wolves properly. So if you put the wolves the same into probably in India where there is no ice there, it will clearly say it's not a wolf, but it still turns out to be a wolf. So you need to be very, very careful of what is the final feature vector that's being used to get the final output. Okay. So yeah, these are some of the practical issues that I'm trying to tell you, uh, because you probably will be using it next few months since you have done this course. So yes, there are neural networks, and now we just check that we need a convolutional neural network instead of the usual neural network for this specific kind of data where we have correlation between the adjacent values. And there could be max pooling layer, for instance, because max pooling helps to decide whether, first of all, it reduces the size of these filters, or and then on top of that, it helps deciding whether some particular pattern exists or not. That's why max pooling helps. We'll do a question on max pooling, so it should be clear when we do it. Okay. And once this is done, why why deep neural networks? Deep neural networks, you can they initially they were started with the function that we discussed earlier, which is the sigmoid function. But as you can clearly see that after a particular range, the gradient will be zero, maybe plus minus some delta from zero. If you go ahead after that, or you go below that, you see that these gradient values goes to zero. Once the gradient values goes to zero, the training stops because everything is based on gradient computation. So there are other activation functions like tanh. Tanh is also looks similar to the sigmoid function, but it also has the same problem that it can't have uh, gradients after a particular range. So yeah, tanh looks like this. So again, if you go in after these in this direction on or in this direction, you see that the gradient will almost be zero because it's a flat region. Okay, so once this is done, someone came up with ReLU, which is rectified linear unit. So once you have rectified linear unit, it was made sure that if your data is greater than zero, so f of x is equals to x for x greater than zero, or it is zero for x less than equals to zero. So this is ReLU of x versus x. So what's the advantage here is that, see, here you see most of the values are saturating at the point. So if you constantly multiply, for instance, in case of sigmoid, everything lies between 0 and 1. If you constantly multiply, keep on multiplying gradients which lie between 0 to 1. So something x to the power n, where x is less than 1. For instance, if x is zero point 0.1 and if you multiply it 10 times, it turns out to be very small. It turns out to be really, really small. So your gradient dies as soon as you increase the number of layers. But in case of ReLU, the gradient doesn't die out because now you have gradient directly proportional to the input x. Well, it is just x here, x, yes. So if you have here x greater than, so your x here is gradient value. So I should maybe just rewrite it in some other, maybe I'll write g to the power n. So these are all gradient values. So gradient is zero point 0.1 10 times, then it goes like this. So here the gradient, as you see, is good enough. Well, it's actually 45-degree here in this case. So the gradient is, the slope is 1, gradient, no, the slope or the gradient here is 1. In this case, it is the slope. So yes, it won't die out. You can clearly see that it won't die out. Of course, now this will be weighted by all other things that are present there because you have all the connections possible here. Once you have that, you can make sure that your gradients are working enough for the specific input. And there are other activation functions as well, like relaxed ReLUs or leaky ReLU, where you see that they have added like this. Instead of keeping it 0 for negative, they keep some other slope for negative, which is not as great as the positive slope. Anyways, that's not the point here. The point is we are able to now propagate the gradients to a more number of more number of hidden units. So that's why we can have deep models. Deep models arise mostly initially because of ReLU. Okay, so after this, autoencoders were done. Can anyone tell what is autoencoder? So it is also for unsupervised learning. Do you agree with that? You don't have explicit labels, you just have inputs. That's all. So once you have inputs, you want to do something with it. So a very uh, common diagram that's used for autoencoder is like this. So this is the encoder part, and this is the decoder part. So here we have input, and we have reconstructed input. So what we want is this input and this reconstructed input should be as close to each other as possible. Well, of course, our input is fixed, so that means your reconstruction should be as close to the input as possible. Okay, so why we are doing this is because of this useful part of it, which is the latent variable. People generally call it as latent variable, or in the course, it's also called as the code. So what we are trying to do is we are trying to map this high dimensional data into a low dimensional data. Once we have this low dimensional data, we again try to reconstruct back the original data. Why this is useful is because first of all, if you have a noisy image, in case you have a noisy image, your low dimensional data will remove the noisy part of it. And once you come back, you might get a image which is less noisy or completely noiseless. So that's why it's useful. And the second way you can use it is tweak, you can train all the images as input and reconstruct the inputs. Once you have trained it properly, you can just remove the encoder part. That means this part is removed, and this latent variable, you have to make sure that it follows the Gaussian distribution. Once you make sure that it follows a normal Gaussian distribution 0 and 1, what you need to do is you can just take samples from this distribution and give input here at the decoder, start of the decoder. Once you give the input at the start of the decoder, what you have is something different than what you have seen in the input. So this can also give you a generative model. So it has two advantages. One is uh, applications rather. One application is image denoising, any any signal value. It's not specifically image. And the second is generative model using only decoder after training. And the second application has been used a lot in research and it's currently exhausted. But this has been more popular than the first one, just for your information. Okay. So once you have this relationships, you have many other sorts of uh, you have other sorts of uh, models as well. But I think we'll close our discussion here and then start solving questions. Okay. Any doubts till now? Okay, then I think we can start our question for today. So our first question is this. Uh, yeah, an input feature map of dimension. This is passed through a two-dimensional convolution layer. A total of 64 filters of size this yields a feature map of this dimension. Determine the number of parameters. So, can anyone tell how to proceed? Anyone? So, what it is saying is, someone has given some input image, and then there are a few convolutional layers. So, at some convolutional layers, the input is 74 shots cross 74 cross 32, and you have another 2D convolution layer. I'll put it slightly far away. Okay. This has the output of 72 cross 72 cross 64. Okay. So what what you have is this size is 64 which is given to us. There are 64 filters and each kernel size is 3 cross 3. So whenever you take a 3 cross 3 patch and then you apply. Yes. So how to determine the number of parameters? How do you do it? So we have 3 cross 3 patch, right? So for each 3 cross 3 patch, we'll have weights W1, W2, W3 up to W9. Yes. So each 3 cross 3 will have 9 parameters, which is, yeah, 3 into 3. And then what is the width of the previous layer, which is 32. So the number of uh, parameters per filter is what? 3 cross 3, and you have to cover all the 32 uh, previous channels or previous filters. So you have this many plus a bias term plus 1. So one filter will have 3 into 3 into 32 plus 1. So your convolution filter will look something like this. So each of them will be 3 cross 3, and then there are 32 of this, and this is a This part is 3 cross 3. Okay. So the number of parameters per filter is 3 into 3 into 32 plus 1. This is for the bias term. So this is what gives you that W transpose X plus B, or this W transpose X can be written as W1 X1 plus W2 X2 as given in the class. Okay. So X is your input, uh, which is which are the values here in this uh, previous layer. W is this whole convolution weights, and the bias term is 1 per filter. So now we have 64 filters. That's why your output size is 64. So what is your total number of parameters? Total number of parameters is 3 into 3 into 32 plus 1 whole into 64. So this turns out to be this specific number, 18496. Okay. Is this question clear? Any doubts in this question? So what we did is we just took the patch size, which is 3 cross 3, and we checked the previous dimension, which is 32, in the channel dimension, which is 32. Once we take this 3 cross 3 cross 32 is the number of weights that we need plus one more for bias term. This is the total number of parameters required for one filter. That means just one of them, like this. But there are 64 of them here. So we'll just multiply it with 64, and what gives us that gives us the answer. Okay. Okay, I guess this question is clear. We'll move on to the next one. So we consider a standard three-layer backprop net with d-dimensional input. Once we have d-dimensional input, NH hidden layers, C output units, and bias, find the expression for output node at K. Okay. So what is this? What is it that we need to do? Anyone? We need to find the expression for the output node K. So we'll try to see it in terms of a diagram. So there are D inputs because it's D-dimensional input there, and there are these are NH hidden number of hidden nodes, and once we have this, and we have C output nodes. So these are C in total number. Okay. So once we have this, we know that for the standard backpropagation network, we have it's a fully connected network. Yes, the same thing here as well. Standard neural network implies fully connected network. Okay, so once we have this fully connected network, we'll try to get what are the outputs at each of the layer. So we'll start from this layer, this output layer. So maybe I'll write it as output O. So let me write indices. I'll use index I for the input layer, J for the intermediate layer, and K for the output layer. Okay, to make things clear. So once we have this, I'll write this output, intermediate output as OJ, and input I'll Input I'll write it as xi, and output I can write it as probably yk. Okay. Okay. So now what we need to do, we need to get the expression for output node at k. So we'll first see how the OJ looks. How will the OJ look? So what this thing does, takes all the inputs, weights it with the weight parameter that you see, that is, uh, I will write it as Wij, since it's connecting ith node in the input to jth node at the hidden layer. So, and here it will be Wkj or Jk. Yeah, here it will be Wjk. Yeah, here it will be Wjk. Okay. So once we have this, what it does is it takes all the inputs, weights it based on the weights of the neural network, and then sums it, add the bias term. Once we have the bias term, we just we add the bias term as well in this, and then we add a nonlinear function. Once we add a nonlinear function, we get the output OJ there. Okay. So what we did is we'll first take all the inputs. It should be I, because I chose I as the input index. I equals to 1 to D because there are D number of inputs. Wij from it, connecting input node I to the output node J. Once this is there, into Xi, because ith Wij means ith node is connected to ith input node. The ith ijth weight is connecting the jth vector, jth hidden node to the ith input node. And then once we add all those things, we add a bias term. I will write it as W0, and this is specific to the jth node of the hidden layer. And then we add a nonlinear function f. So f is the nonlinear function. So this is how it looks for the intermediate output at the hidden layer for jth node. Okay. So now once we have this, what we need to do, we have to do this again, but now for the output layer, final output layer, that is the layer which contains yk. So now my yk will again, what it will do, it will take the output from each of these intermediate hidden nodes, then weight it with the respective weights of the neurons, add the bias term, add everything together, take add nonlinearity to the whole expression, and then gives you the output yk. So it looks similar to this. So it will be summation over j equals to 1 to nh. Nh is the number of hidden layers. Wjk, which is the weights that we defined there, into oj. Oj is the output at the hidden layer. So we sum all of this, and we add a bias term for each of the kth neuron, output kth neuron, and then we add a nonlinearity f. So we assume that we are using the same nonlinearity everywhere. So that's why we use f here as well. Okay. So now what we know, OJ is given from here in this case. So we'll just replace the expression from the above. Wjk into OJ. OJ is f of summation of I equals to 1 to D Wij xi plus W0j. And this is OJ, and this is the whole thing gives you the output. This is how the YK looks. Okay, final output. The output output at kth node. And finally, last layer. Okay, is this thing clear? Any doubts with this thing? Okay, I think there are no doubts with this question. We can move on to the next one. Uh, yeah. So express the derivative of a sigmoid in terms of the sigmoid itself in the following case for a positive constant a. Okay, so what I have the expression here is f of x, which is a sigmoid function. Uh, yeah, it, it looks like this, e power ax. Actually, there is a minus, but here in the specific question they gave e to power ax, so we'll consider this. So this is the function given to us, and we have to express the derivative of sigmoid, that means derivative of this function with respect to the as a function of this itself. So what we need to do, we first take the derivative. How do we do it? F dash x is del f by del x. Now here it's not partial, it's complete because there's only one variable. So df of x upon dx. Okay. So d by dx of 1 plus e to the power ax whole to the power minus 1. This gives us minus 1 times 1 plus e to the power ax into e to the power ax into a. This is minus 2. Yes. So everyone agrees. I'm just applying chain rule. So I just replace this expression here. So what happens to the power? Power comes down and then you have to decrease the power by 1. That's what I did. And then now checking the internal expression, e to the power ax, the derivative is e to the power ax. And now take the derivative of ax. It gives you a. So how does it look? Minus of a e to the power ax upon 1 plus e to the power ax whole square. Okay. So now we have to write it in terms of f of x. Write this expression in terms of f of x. So you can clearly see that one f of x we are already getting here. And what about 1 minus f of x? Now we are trying to get the other f of x here. So 1 minus f of x is 1 minus 1 by 1 plus e to the power ax, which turns out to be e to the power ax upon 1 plus e to the power ax. Okay, so this is very clear. Once this is there, what I can see is I can write f dash of x as minus a into, if I take f of x here, maybe I'll just write it for ax like this. This turns out to be f of x, and I can write this separately e power ax upon 1 plus e to the power ax. Okay, this is minus a times f of x into 1 minus of f of x. So this is the answer. Any doubts? Okay.
No, this is clear, Palak.
Yeah. Okay. We'll move on to the next one then. Okay, so we have inputs x, y, and z given to the network below. Once we have these inputs, we need to compute the gradients of the output. So this part is the output, by the way. Yeah, this part is the output, and we have to get this output. Maybe I should write something. Yeah, I'll label it as variable p, which is the output for this network. And we need to find the derivative of p with respect to x, y, and z, output p. Yeah. So how do we proceed? First, what should we what should we do? At first place, we need to decode this block diagram. Yes, everyone agrees with that. Okay,
Yes.
copy that again so that we can use it. So what does this say? This is addition operator.
Right. Right. Right.
Yeah, this is addition, and this is also the same as addition, and this is multiplication. Okay. So once we have this, what we need to do, we'll just trace the operations. So here we have to do x equals to 2. That is fine, but we'll first write in terms of the variables itself. So what this gives here is x plus 1. This is x, and this 1 is added, which is the bias term here. Once we have this, next is the inverse operation. What will it look like? X 1 by x plus 1. Inverting this will look like this. Okay. So when doing this on a computer, you have to make sure that your x is not equal to minus 1. You have to limit the inputs in such a manner. Otherwise, it will give you runtime errors. So once we have this x plus 1, yeah, once we have this x plus 1 expression here, 1 by x plus 1, we have to multiply it with y. So here what we get is y upon x plus 1. Yes, and then we multiply. Oh, multiplication is done, and then we have to do addition here. This expression added with z. So our output is y by x plus 1 plus z. Yes, yeah. So I'm calling this as p, just for easiness. Okay, so what I need to do, I need to get the gradient. Okay, so it's del p by del x. So here I'm taking partial derivative, that's I'm using del. Otherwise, previously I used the d operator directly, d by dx. So del p by del x, what it should be. So y is there, so x to the power, x plus 1 to the power minus 1, right? So minus 1 will come down, and this will be x plus 1 to the power minus 2. And this is a constant with respect to x, so it's 0. So your expression looks like minus y upon x plus 1 whole square. This is with respect to x, and now we'll do it with respect to y. Y looks very simple. This is 1 by x plus 1, and the last one is del p by del z. Yes, okay, this gives us 1. I hope this is very simple. So once we have this, what we need to do? We are given inputs x equals to 2, y equals to 3, z equals to 1. So go y equals to 3 and z equals to 1. And yes, yeah, here we don't have dependency on z, so it's good. What we have is, so our final vector, which is like this, the gradient vector will look like this, del p by del x. del p by del y, del p by del z at x equals to 2, y equals to 3, z equals to 1 is what? So we'll place x equals to 2 here. Yeah, 2 plus 1, 3. And y is 3. So this is minus 3 by 3 square. And this x is 2. So 1 by 2 plus 1 is 3. And the z is 1. So your final answer will look like minus 1 by 3, 1 by 3, and 1. Okay, this is what they needed. Get into the output reflected finally. So this is the final answer. Okay, any doubts?
No.
Okay. Okay. So yeah, here the only part was to track the operations. If you track the operations correctly, the question is very simple. We will now move on to the next question then. This is a slightly bigger question. Let's see how to copy this. How it got copied. Okay, this is very bad. Hmm. For coherent self-organizing map to cluster four vectors, the online vectors to be clustered are sequentially given like this. So the online vector in sequence is like this. The first vector is 1 1 0 0. The second is triple zeros and then 1. The third is 1 and triple zero. Fourth one is double zero double one. Okay, so these are the four vectors given to us. And the maximum number of clusters is m equals to 2. The learning rate is alpha t, where alpha of 0 is learning rate, alpha of 0 is 0.6, and alpha of t plus 1 is 0.6 times alpha t. Okay. And we have also been given the initial rate matrix. So the initial rate matrix looks something like this. 0.6, 0.8, 0.7, 0.6, and point. Okay. So after the first iteration, how will after the first iteration to cluster this vector, that means we'll first go through this vector and then this second vector and then this third vector. Once we have gone through the third vector, how will your uh, weight matrix look like? How will the weight matrix look like? So yes, so what kind of problem is this? Is it supervised or unsupervised? Anyone? So what's the aim here?
This is unsupervised.
Okay, yeah, it's unsupervised. So what's the aim in this case?
We have to find the winner neuron and adjust the weights and
Yeah. So ultimately, you want to cluster. So clustering
cluster.
is the,
Yeah.
yeah. So uh, any clustering problem is generally an unsupervised problem. You don't have labels of which cluster the specific uh, input data belongs to. If you have labels, then it will become a classification problem. Instead of clustering, then you will try to classify whether a particular vector belongs to a particular class. Okay. Yeah, it's an unsupervised problem, and it has some other advantages than the other methods that we saw, which is here everything is compared with respect to the input vector itself rather than the weight vector, which in some sense helps to preserve the topology. So if we look for the specific case, it will be like this. These are the four input vectors, and we want to classify it as what? These are the classes, class labels. So what we need to do is, of course, as we know, we'll have all possible connections. Uh, yeah, this is all possible connections for y1. The first class, this is all possible connections for the second class. Once we have this, so this is how your neural network should look. And what you're doing is you're trying to learn the weights here, wij, the weights here. There'll be weight here in all the connections that you see. And these weights will, as someone said, these weights will be updated based on the input data. Okay, so we'll look into it on how to proceed. Hmm. So we have been given the initial weight matrix like this. I'm just rewriting it. So yeah, so this is the weight matrix given, and we have to go sequentially because it's an online method. So first we'll go through this vector, which is x1. I'll just label it like this. So first we'll go to the x1 vector, which is 1100. So what is it that we need to do? We'll compute the, uh, maybe I'll just call this as w1 and this as w2, which has its own elements. Okay, so we'll find the distance between w1 and x1 and w2 and x1. So this is our input. Yeah, so this is our input. So so this d of 1 is our distance between the current input x1 and w1. Okay, maybe I should use a better notation. D of x1 with respect to the first class. Okay, so I'll take the square distance instead of the Euclidean distance. So what it does is we don't have to take the square root again and again. So what I'm doing is zero point 0.3 minus 1 whole square plus zero point 0.4 minus 1 whole square plus zero point 0.6 minus 0 whole square, zero point 0.8 minus 0 whole square. So this is the distance of x1 with respect to the first vector. This comes out to be 1.85. Okay, so I'll do the same thing d2 with respect to x1, which is zero point 0.7 minus 1, oh sorry, zero point 0.7 minus 1 whole square plus 0.2 minus 1 whole square plus this is same 0.6 square plus zero point 0.3 square, and this will turn out to be 1.03. So once you have these two distances, you can clearly see that d1 of x1 is greater than d2 of x1. So which one is the winner? Class 2.
W2.
Yeah, class 2 is the winner. Or rather cluster 2, I should not say class 2 to be technically correct. Yeah. So the cluster 2 is winner because it is near to the given input x1. Once you have this, or how do we update? So W2 will be updated as W2, the current value, plus some alpha times x1 minus W2. Yes, so x1 is our current input, so that's why I'm using x1. Or at the ith iteration, it will be ith xi minus W2. So what is W2? In our case, it is 0.7, 0.3, 0.6, 0.3. Okay, 0.7, 0.3, 0.6. And alpha is for the whole first iteration, it is 0.6. Alpha 0 is 0.6. Okay, so it is 0.6 times, what about x1? X1 is 1100, right? Yeah, and W2 is 0.7, 0.7, 0.3, 0.6, 0.3. So if we just compute these values, it turns out to be uh, this much: 0.88, 0.72, 0.24, 0.12. So this is how we updated W2. This is the new W2. So our weight matrix now looks like what? The first column will be the same, 0.3468, and the second column will be replaced with the new values. Okay, now we'll take the second sample, which is x2. X2 is 0001. I should write this. Okay, the first sample. Yeah, now we'll take the second sample. X2 is 0001. So similarly, I'll compute D1 from x2. So I'll take these values and then subtract it. It is 0.3 square plus 0.4 square plus 0.6 square plus 1 minus 0.8 squared, which I think I computed it to 165. And d2 of x2, which should be 0.88 squared. First one 0.88. Second one is 0.72. The third one is 0.24. And the fourth one is 1 minus 0.12 squared. So adding these things will turn out to be 1.96. So here again you can see that the okay, it's not the same. So d2 of x2 is greater than d1 of x1. So cluster 1 is winner in this step. Once you have cluster 1 is winner, you have to update W. So whichever is the winner, you have to update that. So your W1 will be updated as W1 plus alpha times x2 minus W1. Okay. Well, here we are still going through the first complete iteration. One iteration completes when we go through all the samples, so that's why We will not decrease it with zero point 0.6 times zero point 0.6. We'll only use this 0.6. Okay. So given the values, what are the values of W1? We must replace it here 0.346, okay. 0.3, 0.4, 0.6, and this is zero point 0.6 times x2. How did x2 look? 0001 times this minus 3.4.6.8. Okay, so this is how W1 looks. We'll rewrite it. This 0.12, 0.16, 0.24, and 0.92. So once we have this W1, the new weight matrix turns out to be this one. So we'll replace the first one since we updated it. The second one we did not update it, so we'll just retain the one that we got earlier. It looks like this. And then finally now the third sample. The third sample is 100. Okay. X3 is 100. So what we'll do is we'll just use the same scheme d1 of x3, which is 0.12 minus 1 whole square plus 0.16 square plus 2 whole square. Yeah, this is a bit lengthy question, I understand, in terms of computation, but I'll just finish it. Okay. d2 of x3 is 0.88 whole square plus 0.72 square plus 0.24 square plus 0.12 square. Now this turns out to be smaller. So it means d1 of x3 is greater than d2 of x3. So cluster 2 is the winner. Update W2. Okay, so our W2, okay, our W2 will be W2 plus alpha times x3 minus W2. Okay, so this is 0.88, 0.72, 0.24, 0.12 plus 0.6 times 1,000, same thing. And this gives us the final weight vector for the second cluster as 0.952, 0.29, 0.096, and 0.04. And probably the numbers are correct. That's what I hope. So, yeah, your final weight matrix is what you should check in the options during the exam. 0.12, 0.16, 0.2. So this is the final weight matrix. So this is your final answer. Any doubts in this question? So I'll just do a short summary of what we did. So in the Kohonen self-organizing maps, what we need to do is, given the input data, which is in a specific sequence, we would like to cluster the input data by updating the weights for each of the clusters. So our diagram will look something like this, where input nodes are like this and output nodes are like this, and we have all possible connections since it's a neural network, the basic neural network. And given an initialization for the weight matrix, that is, if you consider W1 this like this, that means W1 belongs to this, and this neurons. W2 belongs to the neurons corresponding to the second cluster, all going to the second cluster. Okay. And here in this case, we did not consider bias terms because for clustering, we don't consider the bias terms. So now we consider the first sample. What we did with first sample is compute the distance from the first cluster, uh, weight of the first cluster. And the same thing we did it with the second cluster, and the one which is the smallest is the winner, and we'll update the weights of this of the winner cluster. Again, same thing we'll repeat. We'll update the weight matrix. Once we update the weight matrix, we'll again repeat the same thing with the other sample. The smallest one is the winner, and we'll update the weight matrix, and we did it again. So finally, what we get is this final weight matrix after three samples. Okay. Yeah. Okay. So we will move on to the next question. Uh, yeah. So we are given image like this and a kernel like this. So find the output of the max pool layer when the kernel with stride one slides over the image. Slides over the image. Use the necessary pattern. So how to proceed? Anyone? How to proceed?
We need to do padding first.
Yes, that's right. And then
Then move the kernel from the stride is 1. So we will move the kernel by one along the row side and then row wise like that.
row wise, yeah. And then once a row is completed, we'll move on to the next.
And move
Yeah.
on to the next and then find out the max pool out of it.
Yes. So yeah, it looks a bit lengthy. So we'll try doing it soon enough. So I'll just write the matrix first, and then I'll pad zeros. Okay, so this is the input image. So when we pad it, how do we pad it? Zeros. Just write the other color so that looks better. So you have to pad it diagonally as well. So why do we need padding? So that now we can make sure that we can use the corners as well in our specific problem. Okay. So we now have a 3 cross 3 kernel given to us. So so when the kernel slides over the image, what we need to do is we'll multiply the corresponding elements when it is placed at a particular position, and then sum them. So now first I'll place it here. Once I place it here, you have to multiply the corresponding positions. Here it's 0, here it's 0. So multiply 2 with 3, here it's 0, and here it's also 0. So what our final matrix after applying the kernel should be is the original size, which is 5 cross 5. Uh, since this 5 cross 5 and this is 3 cross 3. The we should get the original input image size because we padded it with zeros, the necessary amount of padding. Since it's 3 cross 3, that's why we padded it with one row and one column of zeros. Okay. If it's 5 cross 5, we will pad it with two rows of zeros and two columns of zeros on all the sides, left, right, top and bottom. Okay. So what we need to do, we multiplied the corresponding elements. Here we got it, the first element as 6. Now once it is done, we have stride of 1. So stride of 1 means our, uh, maybe I can use another color. Yeah. So my kernel will now be placed like this. So once my kernel is now placed like this, I'll check for the corresponding elements. The first part is 0, you don't have to care. This is 3 into 6, 3 into 6, and plus 2, which, okay, someone joined, just 2. Yeah. So the first part here is 0. This is 3 into 6, 3 into 6, it's 12, and here it's 0. Here is also 0, here it's 0, and 2 into 1, which gives us 12 plus 2, 14. Okay, so the next element is 14. So I hope it's clear what I'm trying to do. I'm just placing the kernel here exactly at this position, center position, and then seeing multiplying corresponding elements and then summing up them, the whole thing. And whatever is the resultant, I'll just place it here. So my next one will look like this. So here what we have is first row is 0, no problem. 3 into 2, 6 plus 4, 10. It's a 0, it's a 0. 10 plus 1, 11 plus 5, 16. Fine. Or I did something wrong. 6 plus 4, 10. Okay, so it turns out to be 60. Yeah, so you move your kernel like this, slide over the whole image, and you get values here in this fashion. I'll just write out the values to make things clear. I'm just drawing lines so that things don't get mixed up. Okay, and next I'll get 14, 12, 12, 17, 11, 3rd is 8, 10, 17, 19, 13, 7, 9, 6, 14, 12, 6, 4, 4, 6, 4. So this is the output after applying kernel. Let's try one. Okay, so this is what you should get. Yeah, this is what you should get once you apply the kernel and get. Uh, so once you have this, what can we do next? You have to do max pooling. So here the max pooling is to be done on 3 cross 3 patch. Okay, so what we have is 5 cross 5. How can we correct this thing? We have to do something better to make sure that we have a 6 cross 6. What is the easiest way to solve it? We'll just add zeros. Yes. So I hope everyone remembers that max pooling is done on non-overlapping patches. If you have to do max pooling on a 5 cross 5 patch with given size 3 cross 3, it won't help because you cannot really make 3 cross 3 patches with it. So what you need to do is you need to make it 6 cross 6. How will you make it 6 cross 6 is by adding zeros. So once you have zeros, uh, yeah, once you have zeros, what we can do is this is how we can divide the whole image now. Yes, yeah. So once we divide the whole image, what is it that we need to do? We'll take the maximum in each of the parts. So divide the image into non-overlapping parts based on the size of image. And once you have that, what you need to do next is find maximum in each part. Yeah. So what is the maximum number?
Lalit, one
Yeah.
question here. Like,
Yes.
instead of padding here for max pooling, instead of padding here with zeros,
Uh-huh.
if we pad the two rows of zeros in the original image itself, uh, and that is how I did.
Mm-hmm. Okay.
That also gives the same answer.
Yes, it will give you the same answer. Why? Because most of them will be zeros, right? If you have two
Yeah.
rows here, zero, so the response will be very low. For max pooling, it won't affect at all because it will just consider the maximum values, right?
Okay.
So since you're considering maximum values, here you have some non-zero elements here instead of zeros that I wrote in green. So it won't change the answer. But in general,
Mm,
if you have other pooling like average pooling and all, then your answers will change.
okay. Okay. Yeah. Thanks.
So yeah, in general, for practical purposes, people use max pooling and no other pooling is generally used. Why? Because intuitively, if you see, you want the maximum response to be captured for a given kernel and not the average response. Maximum response is somewhat more robust than average response. So it helps to train your neural network faster and the convergence is, you can empirically see that the convergence is fast. Okay, so coming back to the question, in this specific part, what is the maximum number? It is 14. In the next specific part, the maximum number is 17. In the next specific part, it turns out to be 11. Yes, yeah, this one, I'll just probably mark it. And in the last one, it is
19.
19. So your final output should be a 4 cross 4, sorry, 2 cross 2 matrix with these numbers 14, 17, 11, 19. Yeah, so
But
this
this
is,
option was not there in the assignment actually. It was 14, 7, 11, and 19.
yeah, this was wrong.
Yeah.
Sorry about that.
Yeah.
Well, I did not create the assignment, so I really have no idea why are those errors existing. It's something, the translation is happening wrong because someone writes the assignment and sends it to the technical team, and maybe while typing it, it gets it wrong.
Right. Yeah.
Yeah. So We'll move on to the next one. So which of the following is true? Okay, CNNs are invariant to affine transformation. Yes or no? What is affine transformation?
So rotation, translation, and
Yeah,
scaling.
rotation, translation,
Translation, yeah.
translation, scaling, and other effects as well. Whatever we saw. There are other things, not just these three. So the point is, should they be invariant to affine transformation? Just pick one of them. Rotation. If you rotate the image, uh, I have a nice example here, so I'll just copy this. If I rotate it by 90 degrees, for instance, so should your output be rotated by 90 degrees? That means if I just copied this row into this column, this row into this column, this row into this column, like this. That means I rotated the image by 90 degrees. Should the response be rotated by 90 degrees? Anyone?
Could you please repeat your question?
Yeah, so if I see this is the input image, right? The input image, if I rotate it by 90 degree, rotating 90 degree means I'll take this row and copy it into a column. I'll take this row and copy it into next column. I'll take this row, I'll copy it into the next column. So what you are effectively doing is you are rotating it by 90 degree anti-clockwise. So do you agree with this part? How am I rotating? Uh, okay, I guess numbers don't help. We'll just take a simple example. So if I have a nice tree, of course, this is shaded and all. If I have an edge detector now, edge detector will detect what? Just the edges. Yes. Now if I rotate the tree by 90 degrees, my tree will look like this. And if I pass through the same edge detector, now the tree is filled, there are shades and all colors. So here the tree corner edges will look like this. Yes. So it cannot be
Yes.
invariant. Your any
Yeah.
convolution operation should not be invariant. Yes. It should not be invariant. It should change based on the direction because that will help you to get how the edges are. For instance, in this edge detector case. So any CNNs generally capture edges and a higher order uh, objects in the images. So they should not be invariant. So this is false. Okay. So the next one, autoencoders are well-known instance of self-supervised learning. Yes, we just discussed it during the start of the lecture. Yes, it is self-supervised learning because we just have inputs. There is no, there are no final outputs, desirable outputs that we know, and it tries to reconstruct the original image or the original signal and tries to get the pattern so that once we give a random input into the uh, bottleneck part or the random code into it, it gives you some nice output. So they are well-known instance of self-supervised learning. Okay. The next part is dense and convolution layers capture local patterns. Is it true? So first apply a dense layer and then apply convolution layer. Does it capture local pattern? It's the reverse, right? First you
No.
apply CNN and then you apply dense layers. So it applies, well, here the case is the they capture the global pattern in this sequence. This sequence doesn't capture anything. Dense plus convolution. What CNNs plus dense layers capture the global pattern. That's why you can decide on whether, for instance, in a classification problem, whether a particular image belongs to a given class or not. Yes, it cannot just infer just based on a part of the image. So it captures the global pattern. It's wrong, and heterogeneous data triggers very small gradient update. What is this? Is it true or false? So I can just write the gradients like this, right? Wixi, Wij, for instance, xi plus w0j. I wrote the similar expression on top. So heterogeneous data means your xi's are quite different. Even if your xi's are quite different, it doesn't really depend on what the function value of output will be. The output will depend on both the input and the weights. So depends on weight plus input. Yes, so this is also wrong. Yeah, this is the topic. Okay, so is this question clear? So the answer is only one correct answer there. The autoencoders are an instance of self-supervised learning. Any doubts in that? Okay. So there is a next question on XOR gate modeling, which is, to be frank, somewhat complicated. I'll try to explain it to some extent. So, okay, the image is too big. Oh. So you are trying to get XOR operation ultimately using the neural network. So the neural network has this weights and biases labeled as V1 to V1, V9, and how to get the desired network. So how to proceed with this? You can just I mean, there is a hint given here that what operation they want in the specific nodes, right? Based on that, you have to decide what should be the values from V1 to V9. Okay, so of course, everyone now remembers the truth table. It should not be that hard to remember it. So these are the inputs x1 and x2. Once you have the inputs, and will give you zeros after the last one, or will give you ones after the first one. Nor is something that we need. That's why I'm writing it here explicitly. And XOR is similar inputs are suppressed and different inputs are kept. Okay. So how to proceed? We'll first focus on the AND gate. AND gate. So AND has inputs like what? V1 plus x1 v3 plus x2 v5. Yes. V1 plus x1 v3 plus x2 v5. And what are the four possible combination of inputs that we have? 0, 0, 0, 1, 1, 0, and 1 for x1 and x2. So if I place these values here, what do I get? 0, 0 is v1 equals to 0. 0, 1 is v1 plus v5 equals to means that's coming from this truth table. 0, comma 1 should give me 0. and here v1 plus v3 should give me 0, and here v1 plus v3 plus v5 should give me 0. So you need, sorry,
It should be
last,
1. 1.
last bit should be 1. Yes. So what we need is, we need to find hyperplane that behaves like AND operator. Okay. So how to proceed? So you can take what you need. You need 3 points to pick a hyperplane. Yes. You can take any 3 points and start fitting hyperplane. So ideally, take any 3 points and fit a hyperplane. But here the problem is we don't need trivial hyperplane because hyperplane is used for classification in this case. So, for instance, if I take the first, second, and third equation and try to fit a hyperplane, you can clearly see that if v1 is 0, then v3 will be 0 and v5 will be 0. All three will be 0. So that is something trivial that we don't really want to fit because we don't have any information flowing through this. So a non-trivial way to do it is take the last three one. So once you take the last three, what happens? v1 plus v3 is 0. So considering these three, v1 plus v3 is 0, so v5 is 1, and v1 plus v5 is 0, so v3 is 1. So once you have v5 1, v3 1, so v1 should be minus 1. So these are the values that you get for this specific. You take these 3 points. Okay, not considered. Uh, since it gives all zeros. Okay, yeah. So once we have this, what is the expression that we have? V1 is minus 1, V3 is 1, and V5 is 1. So if this is greater than equals to 0, then it should be classified as 1. If it's less than 0, it should be classified as 0. Okay. So to fit a hyperplane in at least 3 dimensions, since we have only 3 variables, we only need 3 points. We don't need more than 3 points to fit a plane. Okay. Again, now we focus on to the or or rather NOR. Yeah. So NOR is, as I see here, it's v2 plus v4x1 plus v6x2. v2 plus x1 v4 plus x2 v6. And if I place again the same values, v2 should be 1, v2 plus v6 should be 0, v2 plus v4 should be 0, and v2 plus v4 plus v6 should be 0. So these ones and zeros are coming from the truth table. And once you have this, again, if you take these three, and these are the trivial hyperplane v2 equals to v4 equals to v6 equals to 0, which we don't need. So what we need to do is we get this one, which is 1, 0, 0. If we take this and solve this, it turns out to be v2 is minus 1, v4 is, v2 is 1, v4 and v6 are minus 1. So the hyperplane here is 1 minus x2 minus x4 greater than equals to 0. Yes. Okay. the important part comes here. So just see the truth table again. So we have initially had four inputs. These four inputs, these are the initial inputs, and what we processed is and and NOR outputs. Once we have these and NOR outputs, so what are the inputs to the next level, the OR level, which is the output of and NOR. Input to next level. Next level means I mean this, and inputs means I mean this. Okay, the color coding helps. So what are the inputs? Unique inputs 0, 1, 0, 0, and 1, 0. Yes, to the OR gate. Input to the OR gate is 0, 1, 0, 0, and 1, 0. So these are the only possible inputs that you give input to the OR gate. And OR means this is what we get. And this is obtained from 0, comma 0. This is obtained from 1, comma 1. This is obtained from, am I right? Yeah, these both are 0, 0, 1, 1, 0. And this. So these are the initial inputs x1, comma x2 that we give. And this is what it boiled down to after taking what? This is and this is NOR. Once we have these two, this is the OR operation. So ultimately this input is mapped to this output, which the whole as whole gives a XOR operation as a whole. Okay, so there is one confusion here, at least to me. I don't know how the lectures were given. The point is whether they binarize here it or not. If they binarize here, if they binarize it here, then what you need to solve is for these three cases. If you want to solve for these three cases, it is V7 plus V8 times, I'll keep this as X3 for now, and this is X4. So we'll solve for V7 plus X3 times V8 plus X4 times V9, where this is X3 and this is X4. And if I place 0, comma 1, 0, comma 0, and 1, comma 0 here, yes, yeah, 0, comma 1 gives me X3. This is X3, comma X4, by the way. I place this here. V7 plus V9, this is V7. This is what? This should be 1, this should be 0. Yeah. And the last one should also be 1. So placing V7 plus V8 should be 1. If I take this and solve it, since we have only 3 points, you can easily solve it. V8 and V9 should be 1. This should be the answer. But if it's not binarized at these levels, then we have to think a lot more than what I wrote here. And to be frank, I did not find a hyperplane which really does this operation, XOR operation. I did not find any correct options in the question. Yeah. Yes, so from V1 to V6, all the options are fine. These are the correct. Yes, these are the correct values. But for V7 to V9, these are the correct values if you binarize it. But I don't think they have binarized it. That's why their options seem to be different. So in case you have doubts about this question, then you should post it on the forum. You should be able to hear from the official TAs of the course. Okay. At least you got the idea that how and NOR operation is giving you a XOR operation. So and NOR together are mapping the four inputs to three unique inputs. The four unique inputs to three unique inputs. And these three unique inputs are then mapped simply by the OR operation to the respective uh, output. So once as a whole, we see it as a XOR operation. Okay. Any doubts on this question? Okay. So there are, I'll just do this one, I guess, last. There's one true and false questions, which I think should be fine. Okay, solving that. I'll do this last question. Okay. So again, CNN has an input volume of 32 cross 32 cross 3, and so the input is of this volume, and there are number of filters is 10, and size of filters is 7 cross 7, which tried 1 and pad 2 side. Which tried 1 and pad 2 slide over the input volume. What is the total number of parameters? Anyone? So as I told, since this is 32 plus 32 plus 3, the first input dimension is 3. So each size of filter, the W's, these are the number of weights that you have. There will be one bias term for each of the as a total. That's why it turns out to be W transpose X plus B, where B is the bias that needs to be learned, or sometimes we write it as W naught. And then you have 10 of these filters. Okay, so filter size is 7 cross 7. The input size, the number of channels in input is 3, so it's 7 cross 7 plus 3, and 1 for the bias, and we multiply the whole thing with the number of filters there. So we note that stride and padding do not add to parameters. Even max pooling, those things don't add to any sorts of parameters. So you don't have to worry about those things. So the final answer should be 1480. Okay. Any doubts in this question? Okay then we can meet next week for the last discussion of this course. Thanks for joining. I'll see you people next week. Thank you.